I'm Richard Hollingham. Welcome to the Planet Earth podcast from a farm near Cambridge, doubling as a hidden lake in Antarctica. I'll explain what's going on in a moment. We'll also be heading out to sea in search of a dead whale.
I guess you could call us grave robbers. We're 1,000 metres down below the sea floor at the final resting place of a 12-metre long whale.
I'm at the test site for one of the most ambitious Antarctic exploration projects ever undertaken. It's called Subglacial Lake Ellsworth and will involve drilling down through more than 3 kilometres of ice into an Antarctic lake. Let me just explain the setup here, and you might hear a few planes go over as well, so quite near the Duxford Air Museum. It looks like a series of giant yellow paddling pools, children's paddling pools, with the largest garden hoses you have ever seen. And they're connected to a series of shipping containers with pipes, flasks, even a boiler in there. And with me is the principal investigator for the study, Martin Siegert from the University of Edinburgh, and Subglacial Lake Ellsworth Programme Manager Chris Hill. Martin, just set the scene for us before we talk about what we've got here. Where is Lake Ellsworth? What is Lake Ellsworth?
Well, Lake Ellsworth is at the bottom of the West Antarctic ice sheet. It's underneath about 3 kilometres of ice. The lake is roughly 10 kilometres long, 2 or 3 kilometres wide, and the water depth of it is about 150 metres. So it's like a rather large Scottish loch underneath the ice of West Antarctica.
Why is it water?
It's very simple. The background geothermal heating is all you really need to get the ice temperature to be at the pressure melting point beneath about 3 kilometres. So
that's water from heat from the rock?
Yeah, it's not unusual geothermal heating. It's just background levels of geothermal heat that you get everywhere on the planet, and that's sufficient to warm the ice to the level that it will melt. And it's expected in Antarctica. We know of about 400 subglacial lakes that are located in various parts of Antarctica. Lake Ellsworth is the one that we're investigating in the next few years.
Why is it so interesting?
Well, there's a number of things that we want to understand about subglacial lakes. It's been 15 years since a breakthrough paper highlighted the scientific interest in subglacial lakes being a place where life might exist, unusual microbes in a very extreme environment, and we're interested in understanding how life can survive in these places, what life exists in these places, whether it's thriving, whether it's on the edge of extinction or what have you. And the sediments on the floors of subglacial lakes might give us very important information about past climate change and ice sheet change in Antarctica.
So what are you planning to do?
Well, our plan is to access and sample the lake water and measure the lake water and get samples of the sediment as well. And to do that is rather difficult because we have to get all the way through that 3 kilometres of ice in a very clean way without disturbing the lake unduly, and getting those samples back to the surface where they can be treated and analysed in laboratories.
Because there might be life there. You don't want to contaminate it, and you want to ensure that if you find traces of it, it's from the lake and not something you put in there.
Absolutely right. There are 2 reasons really to keep this experiment as clean as we possibly can. One is from an environmental protection point of view, because we don't want to disturb this very likely pristine environment that's never been accessed from the surface before. But the science demands that we do things cleanly as well. We're very likely to be encountering very low concentrations of microbes and chemicals that we want to measure. And unless we keep the experiment really clean, all we'll do is measure the things we take down with us, which would be pointless.
Now, Chris, it's your responsibility to make sure this happens.
That's right.
Now, when we talk about drilling down, you're actually using hot water to drill.
That's correct. As Martin said, we have some 3.2 kilometres of ice to get through. Traditional drilling techniques would have used some sort of drill corer, but that takes a long time. And hot water drilling is actually the cleanest, quickest and most efficient way of accessing the lake.
So what have we got here? I mean, these really are really big paddling pools. You've got 2 of them set up at the moment. So they're full of water, and I think it's quite a nice sound when you tap the side. Also, this one's not so warm, but the other one is warm as well. So these are the pools that you have hot water in to drill down.
Kind of. What we need in order to undertake hot water drilling is a huge amount of water. And of course there's loads of water in Antarctica. The problem is it's all solid. So the very first thing we need to do is to get together a large amount of snow in one place and start to melt it. And that's what these pools are for, is to melt some 90,000 litres of water to prime the drilling system to start drilling. Once we are drilling, there's no problem, because as we're drilling down to the lake, we're generating lots of melted snow as we go, which we can recirculate. but we need some 90,000 litres to start the process off.
And you're drilling with this water. It's really a jet of water at the end of these giant hose reels, which you've got trailing across the field here.
That's correct. In simple terms, the system is really straightforward. We take this melted snow on the surface, and the first thing we do is filter it. So, as Martin said, we're trying to do everything in an ultra-clean way. So we filter this water. Then the next thing we do is heat it through a very clean boiler system up to approximately 97 degrees Celsius. We then run it through a bank of high-pressure pumps to get the required pressure, some 2,000 pounds per square inch. And we then basically push this water through a very long hose, about 3.4 kilometre hose, which has a jet nozzle on the end, which just allows us to melt through the ice at an incredibly fast rate.
So, Martin, you've got your hole. What do you then do?
Well, we have to deploy some equipment down that hole and put it into the lake to take our samples and take our measurements. And so we have two items that we'll send down. One is a probe which has sample chambers on it and measuring devices. And that will be lowered down the water column, taking measurements as it does so. It will scrape the sediments on the floor of the lake, and then it will take samples as it comes up. And we'll take that back to the surface and take those samples and contain them and bring them back to the laboratories. The next thing we'll do is we'll put a coring device in, which can take a 3-metre section or core of the sediments on the floor of the subglacial lake. And again, we'll recover that to the surface, pack it up and transport it back to the laboratories.
It sounds to me almost like a space mission where you're sending this probe down into this unknown area. You're not really going to be seeing exactly what you're doing. You can only go to a certain point. Everything's got to be totally clean.
But it has to be clean. We will see what we're doing. We'll have cameras on board the probe and the corer, high-definition cameras, and we'll be seeing that real-time at the surface, so that's very good. But there are some analogies with space science. It is a remote experiment that we're trying to do. It is a clean experiment, as you said, that we're trying to conduct. And it's never been done before, this type of work, so we're having to develop a lot of technology and we're having to solve a lot of problems that we hadn't really imagined when we first started as they come up. There's also another analogy to space science, that the experiment that we conduct in Lake Ellsworth at some stage in the future may well be done in Europa, which is an ice-covered moon of Jupiter with an ocean underneath it. And people speculate that there may be life on Europa. Well, to test that hypothesis, is there life on Europa, will require more or less the experiment that we're going to do in Antarctica. It may be 20, 30, 50 years away or so, that particular experiment, but we're very keen in Lake Ellsworth to make sure that we're documenting everything that we do, such that at some stage in the future, if people want to learn how we did this experiment to help define an experiment for Europa, it'll be available to them.
We're going to talk a little bit more about what sort of things you might find there a little later on in the podcast. But it does strike me you've got an awful lot of goals. You've got an awful lot of things you are trying to achieve.
Two main things, really. Is there life in subglacial lakes, and what do the sediment records tell us about ice sheet history in Antarctica? Those are the main things. To get that information, an awful lot of things have to happen.
You're nodding there, Chris. You've got to make this happen. Now, the experiment itself is due to take place in the summer season, not this next summer season, the following one. So that would be, 2013?
That would be November 2012 through till February 2013, that sort of period.
You've got to get all this kit here. Well, really, it can't have been easy just getting it here to a field in Cambridgeshire. You've got to get all this to a particularly remote part of Antarctica, and it's got to all work, and that probe's got to be clean. You seem to be fairly calm at the moment.
I'm reasonably calm. I have the occasional sleepless night, but generally speaking, we're doing very well. We're on schedule, and everything is running up as we expected it to. So yeah, I'm fairly calm.
Well, thank you both. We'll talk more about life under the ice, as I say, later on. I've taken some pictures of the site here. You can see those on our Facebook page. Just search for Planet Earth online. And this is the Planet Earth podcast. A few months ago, we featured an interview with Nick Higgs from the University of Leeds. Nick studies the worms that feed on bones of dead whales. These Osedax worms can completely devour whale bones on the ocean floor within 10 years, erasing the skeletons of these enormous mammals. As a result, they're thought to be responsible for major gaps in the whale fossil record. To study whale decomposition, Nick has been working with a team from the Monterey Bay Aquarium Research Institute in California. They use a specially adapted ship and remote-controlled submarine, an ROV, to study whale carcasses. Nick's audio diary begins as they head out to sea.
I'm on the top deck of the Western Flyer research vessel, looking back towards the port that we left about an hour ago. The Californian hills seem to rise out of the sea at the moment, almost touching the clouds on this beautifully clear, perfect sunny day. As we left, we were hailed off by roars of sea lions in the harbour, but there's nothing to be seen out here now except for flat, gently rolling seas. Now this ship is a twin hull, which means that the main deck sits on top of two thin hulls sitting in the water, and right in the middle of the ship there's a big hole that opens up, which is where the ROV is deployed from, and that's called the moon pool. Yeah, that is. Now the control room is at the centre of everything we do on the ship. This is where the pilots control the ROV from, the robotic submersible. The room is about the size of a shipping container and has almost 20 monitors in it, and these are our eyes into the deep. The pilots sit up front at the controls, while us scientists sit at the back in comfy cinema chairs, because we can usually be there for about hours at a time, and I tell you that comfort is much appreciated. I guess we're the backseat drivers, so to speak.
Forward for us?
Yeah, you can move forward. X, Y, it's all happening. At each site we visit, we start by launching the robot, which usually takes about an hour before it reaches the bottom. Then we have to locate the whale skeleton on the bottom, which is no easy task. Once we find it, we use the cameras to make observations and carry out surveys, taking lots of pictures as we go. It's probably the most important thing, and pictures really do say 1,000 words. We use the robot's arms to collect samples and then bring them back up. Once the samples arrive, the lab is a flurry and we start examining them as soon as we can, and this usually carries on late until the night until we're absolutely weary but have done as much as we humanly can. What's that guy sticking his head out the tube?
It's a amphipod.
Oh, okay.
I guess you could call us grave robbers. We're 1,000 metres down below the sea floor at the final resting place of a 12-metre long whale. And all that's left of the skeleton is a few bones sticking out of the mud. And right now, the arm of the robot is trying to gently grip one of those bones, not quite sure how big it is, as it pops out of the mud. And we're looking for signs of these bone-eating worms. But from what I can see, they've already done their job, because there's not very much left. And we've got a bone in the arm now. The camera's just zooming in on it. I can see this little red crab who is fiercely defending his bone is now actually following it all the way into the collection box. And there's a lot of mud. You can't really see what's going on. Okay. Well, parts of the bone are very black, which are those parts which were stuck in the mud. So they probably haven't got very much living on them. And the robot arm is just turning around a full 180 degrees, a lot better than my own arm could do. And we're just checking the other surface of the bone, looking for some of these worms. And now we're zoomed in, boy, you can really get a sense of how fast the water current is down here. It's just sweeping past. And no sign of any worms, but there are some more clams stuck to the bone. And it's really chewed up. This bone has been really degraded, probably by these Ossidax bone-eating worms. I'm here in the ship's wet lab, and in front of me I have a small piece of a whale backbone. It's actually a disc from the spine that we brought up earlier. And just over to one side, there are tons of these tiny, tiny little holes in the bone. And coming out of these holes, which I can just see now, are these bright red little feathers. And that's the feathery plumes of these Ossidax worms, these bone-devouring worms. And actually, I say there's a disc of bone in front of me. Half of it is pretty much gone thanks to these worms. And they're absolutely miniature. I mean, only a few millimeters long, sticking out the bones. But you can see it beautifully, these 4 red gill structures that they stick out into the water to collect oxygen. Now my job is to try and dissect some of these out of the bone, which is no mean feat because they have these root tissues that grow into the bone and dissolve it away. And it kind of grows all through the bone. The bone is very spongy, and the tissues grow into that spongy structure So I've got to carefully pick away the bone layer by layer to get at that.
Nick Higgs from the University of Leeds on board ship in Monterey Bay, California. You can hear previous audio diaries at Planet Earth Online. We heard earlier about the ambitious plans to investigate Lake Ellsworth in Antarctica. And before we leave this test site near Cambridge, where the drilling rig has been set up, let's talk a little bit more about the sort of life that might exist under the ice and the implications for life elsewhere in the solar system. And I'm joined by David Pearce from the British Antarctic Survey. OK, so you're going into the ice, into this lake under the ice that's not been touched for, what, millions of years?
Yes, for anywhere between 500,000 and a million years, depending on the rate of accretion of ice on top of it. We're familiar with finding life wherever we look in the biosphere. So if we look in the outer stratosphere, high up in the atmosphere, if we drill boreholes down into the rock, we can normally find microorganisms. And in the cryosphere, the subglacial lake systems are the one place we really don't know what's happening in there. So they're very, very likely to contain life, but we just don't know what it might be and in what form it takes.
What sort of things are you expecting? Are you expecting some bacteria, some microorganisms?
Very much likely to be microbial life in general. All we can do is look at proxies, so things that are like subglacial lake systems. And if we look in the actual ice that overlays the lake, we can get some sort of feeling for what things might have got through into the lake itself. And a similar drilling system over in the continent at Lake Vostok that the Russians are doing have been able to bring back ice samples from quite low in the ice sheet. And those ice samples have contained all sorts of microorganisms that we're commonly familiar with in the biosphere. So there have been eukaryotes, there have been prokaryotes, so the bacteria, there have been viruses, but there's been all sorts of single cellular things as well. From that basis alone, we would expect it to be a subset of something we might already be familiar with.
So you said eukaryotes. They're a more complex form of life than a bacteria. We're eukaryotes, aren't we?
Very much so, yes, we are.
So we're talking something that's more sophisticated than bacteria, but you're still talking single cells. You're not talking fish or anything, giant octopuses or anything like that.
Almost certainly not, no. There are three different main categories of microorganisms. There's the eukaryotes, which include fungi, so the fungi that you're familiar with from everyday environments. There are the archaea, which have only been recently discovered in the 1980s. And there are the bacteria we're more generally familiar with. The jury's still out on whether viruses are living or not due to their chemical structure and composition. But really, the key organisms from our perspective are going to be the bacteria, because they're small enough, they proliferate enough, and they're able and diverse enough to cope with these types of stresses and environments.
And these things would have been trapped there for, several million years, so they could have evolved separately from things elsewhere on the planet.
There are a number of options. The sources could be either migrating through the ice sheet itself, being in situ when the ice sheet formed, or draining in from somewhere else under the ice cap, or indeed coming out of the rock below it. So there's a number of possible potential sources for it. What we do know is that 500,000 years isn't long enough for the evolution of completely new organisms. We might see organisms that have adapted to survive in new ways with novel physiologies, and we might see remnants of populations that have gone extinct elsewhere on the globe, but it's very, very unlikely that we'll see de novo evolution of novel things we haven't seen before.
Now, Martin drew the parallel with this work to looking at the moon of Jupiter, Europa, which, as we understand it, is these sheets of ice, floating lumps of ice, possibly overlaying liquid water.
Indeed. What we do know for sure is that within the solar system, let alone the rest of the universe, there are a number of celestial bodies that have liquid water, and because of the low temperatures, they are encapsulated with an ice crust on top. One of the primary requirements we know for life anywhere is liquid water. So the fact that there's liquid water on some of these celestial bodies out there suggests that if we are going to look for life elsewhere in the universe, they're the best place to start looking. And so for that reason, there's been a lot of interest generated in places like Europa, because we know that there's likely to be liquid water underneath, and the conditions that are found there are likely to be conducive to life should it be present. So it seems like a sensible first stab at looking for life elsewhere in the universe.
Well, wish you luck. David, thank you very much. And that's the Planet Earth podcast. Do have a look at our Facebook page. I'm Richard Hollingham from a farm near Cambridge. Thanks for listening.